The object of our weekend project this time will be the making of a electronic thermostat to replace a broken thermostat in this little heating unit. I bought this heating unit only a few months ago, and as I feared it would, it failed on me just recently, a few days ago. And well, obviously I was rather angry that once again something which you buy fails only after a while of using. Now, okay, I must admit I did use it for quite a few hours every day the last few months, but even then, you know, this is a reasonably new thing, and for it to fail only after a few months is really annoying. Not to mention the fact that if it fails, it might become potentially a hazard. So what we are going to do, because we already know the thermostat failed in this thing, is to repair it by making a thermostat of our own, and possibly even make a slightly fancy thermostat at that, but using only cheap off-the-shelf parts. Okay, so I really don't want to make anything which is really expensive, just reliable and with off-the-shelf, reasonably priced. I hooked up the heater to the main AC via this solid-state relay. Now, I recently bought this on the internet, and I got it for a little bit more than $3. It's a 40 amp solid state relay, you could say, and I could have gone for only a 25 amps, I think, but the 40 amp relay was only, say, $50 more expensive than the 25 amp, and in size it was completely identical. So I went for the 40 amps solid state relay. Now I have it hooked up to the line of the AC, and I'm also leading the power through my multimeter, which is over there, and which will show us how many amps the heater actually draws when we switch it on. Okay, now I'm using my small variable power supply to switch on the solid state relay, and it says that it needs anywhere between 3 and 32 volts DC to switch on. So I will set my variable power supply to somewhere, let's say around 5 volts, and switch the heater on with it. Okay, so I'm going to show you what the multimeter indicates when I switch on the heater. Okay, and I will switch on the heater by throwing the switch on the variable power supply, right? Okay, so here we go. Oh, by the way, if you're ever going to measure current through a device, especially if you're going to measure in the amps, not milliamps but amps range, always make sure you set your leads to the amp position, which you see right here at my thumb, okay? And don't leave it in the voltage plug, because if you do, you might get a serious problem. Well, worst case, you might blow up your multimeter. Okay, and also set it to AC, which I will do by pressing this knob here. Okay, now it's on AC mode. Right, so now keep an eye on the multimeter, and here is the light which would tell us whether it is working or not, the heater. Okay, so here we go. Making contact and throwing the switch over. Hang on, let me switch it on. Okay, making contact now. Oh yeah, it draws quite a bit of current. I would say 4.5 amps, maybe even more. It's rising again. Let's see. Okay, so I would say 4.9 amps. Okay, a little bit less than 5 amps. Right, and as you can tell, I'm switching on the solid state relay with my little power supply. Okay, so if I switch off the power supply, there you go, the heater is off. Okay, so what did this prove to us? Well, first of all, that the solid state relay needs to be able to switch about 5 amps, which it seems to do rather easily. And if I touch the solid state relay, it feels barely warm. Yeah, mildly warm, I would say. So, not hot at all. Okay, and we switched it on with about 5 volts. No problems there. Also, the thing draws about 5 amps when it works. Okay, so at the hottest position, so position 2, which means full blast, full heat, it draws about 5 amps. Which, if I calculate quickly in my mind, means about 1100 watts, which is a lot less than 1500. And this is the inside of the heating unit. Now, I already pulled off the knob, and as you can see, this is the thermostat, okay, which I temporarily bridged. So that the heating goes directly, is switched on directly through the switch and not anymore through the thermostat. As you can see, it's a mechanical thermostat, and that's the part that failed. Now, to unmount it, I need to undo 2 screws at the top. Okay, so here is the overview of the final design. It's still on the breadboard for testing, but it looks okay. So anyway, the thermostat or the thermostat's schematic is over there, and I'm going to give a little bit of explanation, and I'm going to try to explain how it all works in simple terms. Okay, I really don't want to become too technical here, but you could say the heart of the design is this part right here. Okay. Now, this part consists of two transistors, and as you can see on the schematic, I used two MPSA 42 transistors, NPN transistors. Now, the way this works is really like this. So you have an NTC, okay, which is that little round black thing you see over there. Alright? And that little black thing, so the NTC, forms a voltage divider bridge with a potentiometer and a resistance in series connected to the plus, yeah, of the power supply. So the potentiometer is this little thing right here. Okay, right. So what happens is that the divider bridge puts out a certain voltage, and that voltage is put onto the base of the second transistor, of the first transistor you see right here. So the first NPN transistor. Now the voltage is set in such a way that when it hits the base of the first transistor, the transistor goes into saturation, meaning that it almost practically immediately starts to conduct. Now, when this transistor starts to conduct, there is a small current starting to run through this resistor here, and the result of that is a tiny voltage right here, which sets this transistor to conduct. Okay, and this transistor, when it starts to conduct, draws a little bit of current through this resistor here, and then outputs it as a certain voltage. Yeah, and this output voltage we will use later on to control the solid state switch you see here. And in fact, the solid state switch is that thing over there. Okay, so in effect what happens is that this capacitor you see here is being charged up through these resistors, yeah, the potentiometer and the resistor in series. So the current comes here and then charges up this capacitor, which is a 470 microfarad. Now the NTC is in parallel with this capacitor, and in fact what the NTC tries to do, so to speak, is to discharge this capacitor, yeah, in order to make the voltage drop sufficiently so that this transistor stops conducting, this transistor stops conducting, and there is no voltage going to the solid state switch. Now, at a certain set temperature, which you set with the potentiometer, and I stress the fact that it's by no means a very accurate thermostat, okay? It's roughly calibrated for temperatures between, say, 15 degrees C and 22, 23 degrees C. Yeah, so it's and it's really not extremely accurate, but that isn't the goal of the thermostat anyway. The goal is to keep the heater going as long as it doesn't reach a certain set or desired temperature which you set with the potentiometer. But again, this is only very, very approximate, okay? So you could say it's either hot or hotter or cooler, and that's about it. Now the NTC, as I said, when it starts to warm up, its resistance starts to drop, which means that it starts to draw the potential which is at the cross points of the divider bridge. Yeah, this voltage here starts to drop. Yeah, and since this is an NPN transistor, once the potential, the biasing, you could say, of the base is sufficiently negative, okay, the transistor will stop conducting, and of course by that no current will be drawn through this resistor, so this transistor will stop conducting, and therefore there will be no voltage at the output here, which can keep the solid state switch switched on, so thereby cutting off the heater. Now the capacitor you see here is I inserted here because I didn't want this transistor to switch on or off at any sort of spurious signal or spurious voltage drops or even sudden temperature changes. Okay, if say you open up the door and suddenly the NTC is being cooled down again, well, you know, thanks to this capacitor, the switching will not start to switch erratically on and off, on and off, on and off. This capacitor will sort of filter any spurious signals. So the switching will be smooth. That's the word I was looking for. So this really makes for a smooth switching. Okay, so the part I just explained to you is this part right here, okay, in this area here. Now, connected to it all, there's also, you could say, a kind of display, which is this part here. And that is built around a chip which I bought on eBay, and it's a Chinese design chip which let's say found its inspiration in an LM3914, you know, those chips they use to build LED UV meters. So the KA2284 is, let's say, the little brother of that chip. It has 5 LED outputs, and it's really extremely simple to use, and it only needs a few millivolts really to make it work, and to make the LEDs go on, yeah, or off in this case, depending on the strength of the input signal. Now normally the KA2284 is used for VU meter, but you can use it to measure DC as well. Now the way it works really is that as the input voltage or the signal voltage rises, so goes more positive, each LED you see from left to right, so from pin 1 to pin 6 actually, pin 5 is ground, goes on. So each time an LED goes on, the previous one goes off. Now I must say the chip isn't really very accurate, and it has a tendency of to jitter a bit. Which I mean by that is when the voltage is somewhere in between two comparators, the LEDs seem to blink a little bit. So it's a cheap chip and it does what it needs to do, but it's jittery and not very accurate. Still, for our purposes, it will work perfectly. And like I said, it's also cheap. So, here you go. That's the little display I built. Okay, and what it really does is it shows you how the temperature evolves as sensed by the NTC. So once the NTC is up to the desired temperature, the LED on the right, which is this one, and it happens to be a red one, will start to burn. So in other words, when the NTC is cooler, each LED you see from the right to the left will start to light up. So the second one is a green one, and then you have three little ones which are blue ones. Okay, so well, let me show you quickly how it works. Okay, at this moment the temperature in the room is 22 degrees Celsius. So, and since the thermostat is calibrated to work to a maximum of 24 degrees Celsius, well, it indicates quite a bit. Okay, so you see the 4 LEDs, so the 3 blue ones and the green one are lit. Now, just for your information, it draws about a little bit more than 18 milliamps of current right now at 5 volts. At 5 volts supply voltage. Okay, so now this will go rapidly. Okay, so if I bring my hand close to the NTC, watch the LEDs. There you go. Okay, so the blue ones went off. The green one is trying to go off. Yeah, okay, but if it were just a little bit warmer, the green one would go off also, and only the red one would be left switched on. Now, as the maximum temperature which I set with the potentiometer has been reached, you can see the LED, which is that little round thing you see there at the lower right corner of the solid state switch, is off. Okay, so meaning that it doesn't let through any voltage, AC voltage on its output pins. the two pins you see at the top. Okay, so now watch this. So I will take my finger off the NTC and watch the LEDs. Yeah, it takes a while, of course, to react. Well, like I said, the room is pretty warm, so let me create a little bit of air current around the NTC to cool it down a bit. Oh, this is typical. Okay, there we go. Okay. So, okay, it takes a while, but obviously, like I said, the room is now at a cozy 22 degrees Celsius. So, obviously, the thermostat would react only very slowly. And you see that the solid state switch is now on again. Okay, so in other words, as long as the LED display shows you either blue or blue and green, it senses the temperature, the environment temperature, as too low and switches on the heater. As soon as the heater has indirectly heated up the NTC to a certain temperature, all the LEDs except the red one will go out, like this. See? So, the point being that it's not extremely accurate, but it does what the mechanical thermostat did, namely allowing you to set a very rough kind of heating setting and then letting the blower blow hot air into the room until the thermostat reaches a certain temperature and just opens. Yeah. And that's exactly what we built here. Right, I built a small power supply, which you see there on the right of the screen, for my thermostat, and it seems to work just fine. Okay, so the only thing I needed to tweak a little bit was the capacitor and the resistor. So I used a 47 nanofarad instead of a 10 nanofarad capacitor, and instead of a 1 mega ohm I use a 1.2 meg, which you see here. Okay, so it's fairly conventional. I've used this kind of power supply many times, and as long as the circuit never exceeds, say, 35 milliamps, it'll work fine. Yeah, just don't expect a power supply like this to supply several amps or something like that, okay? As long as your circuit doesn't use more than, say, roughly speaking 35 milliamps, you should be just fine. Okay, so the last thing I want to show you on the breadboard before I start to transfer all the parts to a PCB is this. A fuse holder, actually. So once again, I had a good look inside the appliance which I'm going to build in my thermostat, which I'm building here. And what do you know, it doesn't have a fuse. Now, you know, it really upsets me to know that you buy an AC appliance and just to save a few cents they refuse to build in a fuse, okay? And that really upsets me. So what I'm going to do is I'm going to build in a fuse inside the heater, and it'll be a fuse of around about 5.5 amps, okay, or maybe 6, a fast fuse of 6 amp, because you remember we measured the current it draws, and initially when it's cold and you switch it on, it peaks rather quickly to 7 amps or something like that, and then it drops back to 5 amps as it starts to heat. So, well, we'll see. Maybe I'll take a 7 amp fast blow or a 6 amp slow blow. I don't know, but it'll be around that ballpark. Then I'll place a fuse inside the housing, okay? So that the fuse holder itself is rated for 10 amps, so that will do perfectly. In any case, if you ever encounter an appliance, an AC appliance with no fuse in it, then please make the expense of say $50 and install a fuse holder and a fuse, okay? I'd rather spend $50 on a fuse holder and a fuse than have to pay $30,000 on having my house refurbished after it burns down. Alright, I transferred all the components from the breadboard to PCBs, and well, this is the final work, okay? So I haven't tested them yet, but as soon as I rested a bit, I'm going to hook them all up to each other or to a power supply and then test them one by one, just to see whether they function correctly. Okay, so what do we have? We have the display part, which is built around the KA2284, which is this one right here, which by the way is a 9-pin IC. Okay, a bit unusual, but it works. So the 5 LEDs and all the other components, well, the 3 other components necessary to make it work. Okay, so that's the display. Alright, now the next component is the power supply, which is this. Rather classical build. There's nothing unusual about this, except I did make a small alteration compared to the schematic. Okay, the schematic says an 0.1 microfarad. I used a 470 nanofarad. Okay, so an 0.47 microfarad instead. Okay, so and the resistor, the bleed resistor over the capacitor is a 1.2 meg instead of a 1 meg. That's about it. Okay, so all the other components are standard. Okay, so 1N4007, a 50 volt electrolytic, a 5.1 volt 1 amp Zener diode, and that's it. Okay. Oh, by the way, the capacitor is a safety cap. Okay, so if anything happened, a short or an over voltage, so a voltage surge or whatever, the capacitor will blow, but that's about it. Okay, it won't explode, but it'll just rupture. It will cease to conduct. Pretty much like a fuse, you could say. Okay, and then we have the final component, which is the thermostat itself. Okay, so you'll notice that the PCB is rather large, but all the components are crowded in a single corner of it. And then on the other end, there's only the shaft of the potentiometer. Well, the only reason why it is built like that, okay, is because of the allocated space inside the heater. Okay, it doesn't allow for any other type of construction than this one you see right here. Also, I attached the NTC via not too long leads. The leads are 15 centimeters long or thereabouts. Let me see. No, rather 20 centimeters long. But that's okay. I mean, the extra added resistance is negligible. So is the capacitance, by the way. So it doesn't really matter. I did encapsulate the NTC in heat shrink tubing. Okay, the two contacts separately, and then the whole thing with yet another piece of heat shrink, just for safety sake. Okay, and then the last component is the solid state switch, which is this, which happens to be a Photech SSR40DA. Now, there are plenty of brands going around on the internet. I just happened to buy this one, but I'm sure if you look around you'll find plenty of other brands which are just as good as this one, and probably, well, maybe even cheaper than this one. Okay, so actually that's about it, except of course for the fuse holder, which we'll mount separately somewhere inside the heater. First thing to check is the power supply. I hooked it up to the AC, and I hooked the output to my multimeter, and it outputs 5.15 volts. So I would say that's a pass. Now, I have to confess, I had to make a few adjustments, or rather not really so much adjustments as modifications to the thermostat main board, and mainly for this particular reason. The way I had constructed the main circuitry for the thermostat was that you can set a certain temperature at which the thermostat switches either on or off. And I had sort of a fixed resistor in front of the potentiometer, like you can see on the schematic. Yeah, I'm talking about this part here, the divider bridge you see here. Okay, so I made some changes really. Actually, the potentiometer is now a 10K logarithmic potentiometer. Okay, and I took out this resistor here and I replaced it with a small potentiometer in the range of 100K. Okay, you can see it there at the back of hang on, let me see if I can focus. Okay, so you can see the small pot there. Okay, so why? Well, because I experienced that if I use only a fixed resistor, so I'm talking about this resistance here, okay, if this is fixed, there's no way I can calibrate the thermostat. Okay, I really can't. And using the potentiometer's goal is not to calibrate, as it were, the whole device, but is to set a certain level, voltage level, at which it will either switch on or off. Okay, but the potentiometer really functionally has nothing to do with calibration, but all about setting the parameter at which the thermostat will switch. So, excuse me, in order to allow me to do at least a minimal type of calibration, I replaced this fixed capacitor here, which on the PCB was an 82K. I replaced that with a 100K potentiometer, and that allowed me to adjust or calibrate the thermostat. Okay, I hooked up the thermostat to its power supply, and it's live. There's 220 AC now on it right this instant. But as you can tell from the LEDs, the temperature in the room is already quite high. So the thermostat, or rather the solid state switch, is on for the moment. Yeah, because relatively speaking, the NTC is still cool, quote unquote. But as soon as I will start to hold it close to my hand, the NTC will rise in temperature and the thermostat will switch off, and I'll show you. Okay, so here we go, touching right now. There you go, and there you go. Okay, so the solid state switch is off now. Okay, so as you can tell from the LED, it's off, and you can see that the LED over there, the red LED is fully on, and the green one is, well, almost off. Okay, so by the way, a peculiarity of the solid state switch is that it never goes completely to zero. Okay, so, and it actually states that it can switch anywhere between 24 and 380 volts AC. But having tested it now several times, yeah, well, you know, it never goes under 20 volts AC. Now, it doesn't really matter. I mean, under that voltage, the heater will switch off. Okay, so I release the NTC. So in a moment or so, its temperature should start to rise again. To drop again, I mean, and the thermostat should switch on again, which of course, typically speaking, you know, it's always like that when you do a demo. It never quite reacts the way you hope it would. Okay, so okay, well, in any case, believe me, oh, there we go. Okay, so it took a little while, and right, so we're back on full AC, and as you can tell, the LED of the solid state switch is on again. So, my conclusion is that the whole circuitry is tested, it works. So what's left for me to do, obviously, is to build it into the heater. But before I do that, I'm going to encapsulate the bottom of my PCBs, yeah? Well, at least that, and probably parts of the tops as well, okay? So to insulate it at least from accidental contact by humans. Okay, so and I'm going to do that with large quantities of hot glue, yeah, which I'm going to spray all over the circuitry, at least at the bottom of the circuitry. It shouldn't be a problem really using hot glue, because none of the components of the, let's say, none of the modules of my thermostat will be anywhere close to where it's actually really hot inside the heater. So I'm not too concerned about using hot glue, and I'm fairly certain that hot glue has a reasonably high dielectric value. I think keratin is really a very good insulator. Alright, I fitted the system inside of the heater, and you can see the little power supply over there. Okay, and I connected the power supply to the safety switch feature you see down there. Yeah, you see a micro switch, and it's a safety feature. If you knock the heater down, then the switch you see here, I don't know if you can see it, yeah, normally at operation the switch is pushed in, and therefore the heater works. When you knock over the heater, the switch releases, and there's no more power going to the whole of the heater. And I connected the power supply of my thermostat to the output of that switch. So the thermostat is switched off as well. Alright, then I fitted the solid state switch right here in between these two legs, yeah, and I also put a piece of mica between the solid state switch and the heater body. So this is thermal resistant plastic, okay? They wouldn't use this plastic if it wouldn't be able to withstand heat. Huh? That's the same reason why they placed all this wiring at the factory next to this body, okay? So the heat that filters through to the wires can never be that high. Yeah, I would tend to say maybe 30-35 degrees Celsius, and that's about it. So anyway, just out of precaution, I did place a mica shield, and it's, you know, you can buy mica almost anywhere, okay? It's just a thin piece of mica material, yeah, heat resistant material. It's inflammable, and it shields against heat radiation. So I use it all the time to put hot stuff on it, and it has the added bonus that you can cut it with just a normal pair of scissors like this, okay? So it's really useful stuff, and just out of precaution I put a little heat shield under my display module. I did the same for the solid state switch, and I also put one under the circuitry for the thermostat itself right here, okay? So normally speaking, that should be safe. Okay, so anyway, oh, and one more important detail. So this is the heating element, okay? So they call it a ceramic type of heating element. I don't know why they call it ceramic, except perhaps between the resistors you see some whitish stuff, and my guess is this white stuff is indeed a kind of ceramic, and I think maybe the name ceramic heating element comes from that. I don't know, but in any case, what I wanted to say is, so this is the hot surface through which air is being blown, pretty much like a radiator of a car, okay? So the heat is blown through the element and out through this funnel. It's a square-shaped funnel, yeah, which fits exactly over the heating element. So I think actually this funnel was also designed as a safety feature, so that none of the wires or anything would ever suffer from heat emanating from the heating element. I didn't drill a hole or anything like that. The hole was there already, and I suspect that the hole was actually designed at the factory to let in ambient air to the original thermostat, okay, so that it would react to the temperature of the ambient air, okay, because here the air is really at room temperature, whereas of course if you would build the sensor somewhere at the front, you would also include heat coming from the heater itself. Well, there it is, functioning, and it's been working now for, I'd say 20 minutes, and the room is fairly cool now, so I guess it will keep on working for a while longer. A few last remarks. Okay, so as you can tell, I built the display into the casing of the heater. And in fact, I drilled holes and press fitted the LEDs into the holes. So I didn't use any kind of glue or anything like that. I just press fitted them inside the holes. So and that turned out okay. Also, I noted the changes I made to the schematic. Okay, so as you can tell, originally I had inscribed a 500 kilo ohm potentiometer and a 2.7 resistor, drop resistor, and I changed that to a 100 kilo ohm potentiometer, a small pot, and the large pot I changed for a 10 kilo ohm logarithmic potentiometer. So that's really the big alteration I made to the schematic of the thermostat. Okay, so anyway, it does work, and I'm very happy that my design works. The last thing I want to add is, and I haven't mentioned it yet, but as you can tell on my cheat sheet, there's danger here, okay? So if you decide to build the same thing I built, you're welcome to it, but be aware that you're working with deadly voltage, okay? So you're working with AC voltage. And on top of that, you're also working with something that puts out heat. So if you take something like that apart and then put it back together, do it carefully. Check whether there are no wires resting on something that could go hot or make the wire melt or short. Yeah, so you really should be careful if you decide to alter a piece of equipment like I did here, an appliance which puts out heat and uses AC. Okay, so if you decide to do this as I did, you do so at your own risk. Okay, I warn you, be careful and use all the necessary precautions.